Welcome to BioBits and Bytes. Imagine this. You wake up, the scent of coffee fills your kitchen, sunlight streams through the window, and you feel the warmth of your mug in your hands. But have you ever truly paused to wonder how you experience all of that?
Hmm.
What is this feeling of being present, of having a subjective inner world? What fundamentally is consciousness?
It's the ultimate mystery, isn't it? Like trying to understand how a complex symphony orchestra creates its beautiful music by only listening to individual instruments.
Right.
The challenge isn't just hearing the notes, but grasping the whole integrated melody. What's fascinating here is how the seemingly incompatible worlds of biology and quantum physics are beginning to converge in our understanding.
Yeah, that convergence is key.
It truly raises an important question for all of us.
Mm.
Is our everyday experience of reality interwoven with more quantum weirdness than we ever imagined?
Absolutely. Today, we're going to take a deep dive into the very fabric of our conscious experience, exploring some of the most cutting-edge science and theories trying to solve this profound puzzle.
And we've got some really interesting sources to draw on.
We do. Our sources for this journey include comprehensive reviews on consciousness theories, groundbreaking studies on brain activity, and even some highly controversial papers pushing the very boundaries of quantum biology.
Controversial is putting it mildly for some of them.
Yeah. Our mission for you, our listener, is to help you quickly grasp the most important insights, understand the current debates, and get a shortcut to being genuinely well-informed about the science of consciousness, all without getting bogged down in impenetrable jargon.
Trying to make the complex accessible.
Exactly. So let's unpack this. We're talking about the science behind your very own aha moments,
Yeah.
your deepest sense of self-awareness, and perhaps the very nature of reality itself. So to kick us off, what exactly are we talking about when we say consciousness? It feels obvious, something we all intrinsically understand, right?
Mm.
But scientifically, it's incredibly elusive, almost like trying to grab smoke.
That's a fundamental starting point. Researchers often distinguish between two key aspects. First, there are phenomenal fields, what philosophers call qualia.
Qualia, right.
This is the subjective what it is like to experience something. The vivid redness of an apple, the specific timbre of a friend's voice, or the distinct aroma of baking bread. It's the raw, sensory, qualitative aspect of experience.
The pure feeling of it.
Exactly.
Yeah.
Second, we have higher order meta-representation, which is essentially having thoughts about your own thoughts or perceptions.
Okay.
It's not just the raw sensory input, but that reflective layer on top of it, the ability to introspect.
So it's not just seeing a red apple, but being aware that you are seeing a red apple. You're reflecting on your own perception.
Precisely. And this distinction between simply experiencing something and being aware of that experience is absolutely critical.
Right.
It also brings up a fascinating idea of unconscious information processing. Think of it like a complex computer running many background programs you're not actively seeing or interacting with on the screen.
Like background tasks.
Yeah. These processes are vital for the system to function, like managing your internal bodily states or quickly reacting to a sudden sound, but they don't enter your conscious awareness.
Have you ever wondered why you can drive somewhere familiar on automatic pilot and then suddenly realize you don't remember the last few miles of the route?
Oh, all the time, yeah.
That's a classic example often used by higher order theorists. You were clearly seeing the road, making complex decisions, or you'd have crashed, but you weren't consciously aware of it, not actively forming thoughts about your driving.
Your brain was just doing it.
Right. Your brain was processing the visual information and guiding your actions, but that processing didn't reach the level of conscious reflection.
Or consider a more dramatic example like blind sight.
Blind sight, okay.
People with certain types of brain damage might report total blindness in a specific part of their visual field, denying any conscious visual experience there.
Wow.
Yet if you ask them to guess properties of objects shown in that blind spot, like whether a line is horizontal or vertical, or whether an object is an X or an O, they can often guess correctly with surprising accuracy.
Really? Even though they say they see nothing.
Exactly. They might even reach out and grasp objects they claim not to see. This profound dissociation between accurate action and reported perception strongly suggests that our brains process a vast amount more information than whatever enters our conscious awareness.
That's incredible.
It's a compelling piece of evidence for defining unconscious processing and the limits of our subjective experience.
So if consciousness itself is so hard to define, how do scientists even begin to study it? How do they peek inside that black box of the human mind without relying solely on subjective reports?
That's where neuroimaging techniques become indispensable. We're on a quest to find what we call neural correlates of consciousness, or NCCs.
NCCs, got it.
These are the specific brain states, patterns of activity, or properties that consistently accompany a conscious experience. The goal isn't to see consciousness directly, but to observe its neural footprint and understand the conditions under which it arises.
So rather than a full mechanics lesson on each, what are the key takeaways from these powerful tools in our quest to understand consciousness?
Exactly. When we're looking for NCCs, we rely on different tools for different insights. Functional magnetic resonance imaging, or fMRI, is fantastic for showing us where in the brain activity is happening with high spatial precision.
The where, okay.
It reveals which regions light up when you're performing a conscious task or experiencing something specific. Think of it as a detailed map of brain engagement.
Makes sense.
Then we have electroencephalography, EEG, and magnetoencephalography, FEG. These excel at telling us when things happen with millisecond precision, capturing the rapid electrical or magnetic fluctuations of neural firing.
Oh, when? Much faster.
Much faster, yeah. They provide a dynamic timeline of brain events. While they offer coarser spatial detail than fMRI, their temporal resolution is unmatched.
So trade-offs.
Always trade-offs.
Right.
And positron emission tomography, or PET, while having lower resolution overall, is invaluable for quantifying metabolic processes, showing us how the brain consumes energy.
Energy use, right.
Which is a powerful indicator of sustained activity in specific areas. The real insight and the challenge comes when we try to combine these different windows into the brain to map the truly dynamic, multifaceted neural footprint of consciousness itself.
And it's with these precise tools that we're seeing incredible and sometimes heartbreaking things. You mentioned patients who can't communicate. It must be especially challenging to study consciousness in someone who appears to be in a coma or a similar unresponsive state.
Oh, absolutely.
How do you truly know if they're conscious if they can't tell you?
Absolutely. Disorders of consciousness, or DOSI, such as vegetative state unresponsive wakefulness syndrome, VSUWS, or minimally conscious state, MCS, are profoundly difficult to understand and diagnose.
Yeah.
There's a significant and frankly alarming rate of misdiagnosis. Studies indicate that about 40% of patients diagnosed with VSUWS might actually be conscious, but simply unable to respond behaviorally due to severe motor impairments.
40%, that's huge.
It's huge. Standard behavioral scales, while crucial for bedside assessment, can easily miss these subtle non-motoric signs.
So they might be aware, but trapped inside their own minds, fully conscious but locked in. That's a terrifying thought, a neurological lockout that prevents any external communication.
Indeed. It's one of the most ethically challenging scenarios in medicine. This is where fMRI has made incredible, almost revolutionary breakthroughs.
How so?
In some cases, patients who showed absolutely no behavioral signs of consciousness at the bedside were able to follow commands covertly while in the scanner. For example, when asked to imagine playing tennis, their supplementary motor area, or SMA, would activate, just as it would in a healthy person.
Just from imagining it.
Just from imagining it. Or if asked to imagine navigating their home, their parahippocampal gyrus, specifically the parahippocampal place area, would light up. These aren't just random activations. They are specific, intentional, and highly organized responses, mirroring those of fully conscious individuals.
That's truly groundbreaking. It's like finding a hidden signal in the noise, a secret language the brain is speaking, a direct line to their inner world.
It really is.
This must have massive implications for their care, their dignity, and even legal decisions.
Exactly. These findings underscore the critical importance of distinguishing between a lack of behavioral response and a true lack of consciousness.
Yeah.
It poses a crucial methodological and ethical challenge. How do we reliably test for phenomenal consciousness independently of verbal or motor access? Because if someone is conscious but physically unable to move or speak, our traditional ways of knowing their state are simply insufficient. These techniques are providing a vital, albeit still limited, window into that profoundly hidden inner world. It forces us to reconsider what it means to be conscious and how we define life.
So with these incredible tools, scientists are actively trying to figure out how consciousness works. What are the big contenders in the ring? What are the leading theories vying to crack this ultimate mystery of our subjective experience?
Right. There are several prominent theoretical approaches, each offering a unique lens through which to understand how consciousness arises. We can think of them as different operating systems for the brain,
Okay, I like that analogy.
each with its own core principles, strengths, and indeed its own set of criticisms.
Let's dive into the first big one, Global Neuronal Workspace Theory, or GNWT. It's often called the spotlight theory. What's the core idea here, and how does it explain our conscious experience?
Okay, GNWT. Imagine your mind as a grand theater. Most brain activity happens backstage. These are the unconscious processes constantly keeping the show running.
Heart rate, breathing.
Exactly. Regulating your heart rate, managing breathing, or the intricate background processing of vast amounts of sensory data. But when something becomes conscious, it gains access to the main stage, gets put into the spotlight, and is then broadcast widely to other brain systems.
Broadcast widely.
Yeah, this global accessibility means that information can then be used flexibly for various high-level functions, forming long-term memories, planning complex motor actions, evaluating situations, or directing further attention.
So it becomes available to the whole system.
Precisely. The key is that once information is on stage, it's available for many different cognitive modules to interact with and use.
So it's about what information gets amplified, integrated, and shared across the brain, almost like a central broadcasting station for critical information.
Precisely. This global workspace is mainly composed of highly interconnected frontal and parietal areas of the cortex, often considered the brain's executive control centers.
Front and top parts of the brain.
Right, but it also involves subcortical regions like the thalamus, which acts as a major relay station for sensory and motor signals. The theory focuses on conscious access, why certain representations become available for flexible, widespread use in behavior and cognition, enabling us to respond to information in context-dependent ways, rather than just reacting reflexively. Experiments supporting GNWT often show a sudden ignition of frontal and parietal activity when a stimulus becomes consciously perceived.
An ignition, like it suddenly lights up.
Yeah, a widespread burst of activity.
Okay. And then there's integrated information theory, or IIT, which certainly seems to get a lot of media buzz and sparks a lot of debate. How does that one work?
Right, IIT. If GNWT is the spotlight, IIT is more like the unified information theory, or perhaps the teamwork theory, focusing on the inherent properties of the system itself.
Okay, inherent property.
It proposes that consciousness emerges when information within a system like the brain is both highly connected and unified, acting as a single, indivisible whole.
Connected and unified.
Yeah. The more integrated and interconnected the information within a system, and the more causal power it exerts on itself, the more conscious the system is thought to be. It's about how the parts of a system interact to create a unique, unified, and irreducible experience.
So it's not primarily about where consciousness is, but how information flows and combines to create a single, cohesive, and indivisible experience. It seems to be trying to explain the quality of consciousness itself.
Yes, that's a key aspect. IIT attempts to mathematically measure this integration and causal power using a concept called phi.
Phi, I've heard of that.
Phi is a theoretical measure of the amount of integrated information generated by a system above and beyond that generated by its parts. What's fascinating, and indeed highly provocative here, is that it suggests consciousness isn't limited to biological brains.
Ah, here we go.
Yeah. Any complex system, whether a sufficiently complex computer network, an advanced robot, or even a simple organism, could exhibit some form of consciousness, however rudimentary, if it satisfies the theory's criteria for hi-fi.
That raises a question many people immediately jump to. Does that mean my smart refrigerator could be conscious, even just a tiny bit if it gets complex enough? And if so, what kind of consciousness would that be?
It's a key implication, and one that causes considerable debate and skepticism among scientists.
I bet.
IIT proponents would argue that while your refrigerator's phi would be infinitesimally small compared to a human brain, the principle is the same. The theory tries to explain the quality of conscious experience, suggesting that the unique pattern of relationships between elements defines a specific conscious experience.
So the fridge's consciousness would be, what, simple?
Extremely simple, yeah. Perhaps just a very simple, unified awareness of its internal temperature and door state. Critics, however, argue that such implications verge on panpsychism, the idea that consciousness is ubiquitous.
Panpsychism, right. Everything is conscious.
And that the concept of phi is too abstract or difficult to measure empirically, making the theory untestable in practice, at least for now.
Okay, makes sense. And then we have higher order theories, or HOTTs. That's where the awareness idea comes in, right? It feels very intuitive.
That's a great way to put it. ATs propose that a mental state, whether it's a raw perception, a thought, or an emotion, becomes conscious when a lower order mental state is re-represented at a higher order level.
Re-represented.
Yeah. This higher order representation is typically a thought about that lower order state, often thought to occur in the prefrontal cortex. So you're not just seeing a visual stimulus, you're forming a thought that you are seeing that visual stimulus.
Like a meta-thought.
Exactly. It's about having a mental state about another mental state.
So my brain is essentially reflecting on its own perceptions and thoughts. It's like having an inner monitor or narrator that tells me what I'm experiencing.
Exactly. This capacity is crucial for many higher-level cognitive functions. It allows us to make the it seems distinction.
Ah, the it seems distinction, like illusions.
Right. Like discerning between what something is objectively and how it appears subjectively. For example, in an optical illusion, you know what the image is, for example, a flat drawing, but you also know how it seems to you, Virgie, as if it's moving.
Gotcha.
This reflective capacity is also linked to our ability to introspect, to reflect on our own beliefs, to plan, and crucially, to predict or even manipulate the thoughts and perceptions of others.
Theory of mind stuff.
Precisely. It's fundamental for our status as rational agents, enabling us to learn when not to trust our own experiences and to navigate complex social interactions.
Okay. And finally, predictive processing. This one sounds a bit more abstract, almost like the brain is a continuous forecasting machine.
It is, in a way. Predictive processing, sometimes called the predictive coding framework, suggests that the brain is fundamentally a Bayesian machine whose main job is to minimize surprise or free energy.
Minimize surprise, like predict things accurately.
Exactly. Your brain is constantly generating hypotheses about the sensory world, essentially, predicting what it expects to perceive, and then comparing those predictions against the incoming sensory information.
Yeah.
If there's a mismatch, that's prediction error or surprise, and the brain updates its internal models to minimize that error. It's a continuous process of prediction and error correction, a dynamic interplay between top-down expectations and bottom-up sensory input.
So it's like our brain is making predictions all the time for everything we see, hear, or feel, and then updating those predictions based on what it actually receives. Almost like an internal forecasting model that's always refining itself.
Precisely. Higher-level brain regions send top-down information. These are your expectations or context or even internal goals to lower-level regions, shaping how we perceive and interpret bottom-up sensory data coming from our senses.
Right.
Consciousness, in this view, depends on a delicate and balanced interplay of feed-forward, sensory input, and feedback predictions, communication. Alterations in either of these communication pathways.
Like if the predictions are way off.
Exactly. Or if they're too strong and override the senses. That could lead to altered states of consciousness, or even conditions like hallucinations and psychiatric disorders, where the brain's predictions override sensory reality. It's less a theory about where consciousness happens, and more about how the brain constructs our reality.
These all sound incredibly plausible, and they offer different angles on this enormous problem. But with so many compelling theories, is there a way to test them against each other to see which one holds up best to empirical scrutiny?
That's where adversarial collaborations come in, and it's a truly exciting development in the science of consciousness.
Adversarial collaborations. Sounds intense.
It is, in a good way. It's a deliberate scientific approach where researchers from different theoretical camps, who often have very strong, even opposing viewpoints, agree to design experiments to directly pit their predictions against each other.
Okay, so they design the fight together.
Exactly. It's about setting up a fair contest rather than individual labs trying to prove their own points in isolation. A landmark experiment, 7 years in the making, recently did just this for Integrated Information Theory, IIT, and Global Neuronal Workspace Theory, GNWT, publishing its findings in Nature.
7 years. Wow. So after 7 years of careful design and execution, who won? Was there a clear victor in this clash of the titans, or was it more nuanced?
The results were, as is often the case in complex science, surprisingly mixed. It wasn't a knockout for either side, but rather a revealing draw with challenges for both.
Okay, tell me more. What were the predictions?
IIT, based on its core principles, predicted strong, lasting connections and sustained synchronization in the back of the brain, specifically the posterior cortex, as the primary seat of conscious experience.
So sustained activity in the back.
Right. Meanwhile, GNWT predicted greater activity and a distinct widespread ignition in the front of the brain, especially the prefrontal cortex, indicating that conscious information is widely broadcast across the brain.
Ignition in the front. Got it.
And what did this study actually find when they looked at the brain activity of subjects perceiving masked stimuli?
Yeah, what happened?
The study presented stimuli that were either consciously perceived or unconsciously processed and measured brain activity using a combination of fMRI and EEG. What they found posed significant challenges for both theories.
Oh, how so?
For IIT, the evidence for sustained, strong synchronization in the posterior cortex that was unique to conscious perception was not as robust as predicted. There were signals, but not the consistent, high-magnitude integration IIT specifically looked for.
Okay. Not quite the smoking gun for IIT.
Not quite. And for GNWT, while there was some evidence of frontal activity, the predicted widespread ignition in the prefrontal cortex at the moment a stimulus became conscious, and especially its persistence after the stimulus offset, was not consistently observed.
So the ignition wasn't as clear-cut either.
Right. The representation in the prefrontal cortex for certain conscious dimensions was also more limited than expected.
So no clear winner then. It sounds like the data itself is pushing researchers to refine their models rather than unequivocally endorsing one theory over another.
Exactly. The scientific community is buzzing with debate over how to interpret these mixed results. Some prominent scientists have even gone as far as to call IIT pseudoscience.
Wow, strong words.
Yeah, due to its radical implications, its perceived untestability, and what they view as the media's tendency to overstate its support based on these preliminary mixed results.
Right.
IIT's proponents, of course, argue that the experimental setup didn't perfectly capture the subtle nuances of their theory, or that specific measurements needed to be more refined.
Of course. The debate continues.
It highlights the inherent difficulty of conclusively proving these highly complex theories of consciousness when we're trying to measure subjective experience with objective tools. It truly raises an important question. How do we move forward in such a complex and contentious field, especially when the theories have such different foundational assumptions and methodologies?
Yeah.
It forces us to ask, are we asking the right questions or using the right tools?
It certainly seems like the science of consciousness is still very much a work in progress, with lots of pieces of the puzzle still to fit together. It's a testament to the sheer complexity of the brain. Beyond these grand, overarching theories, our sources also delve into how specific brain regions contribute to more defined aspects of consciousness, like self-awareness. Have you ever wondered why you can think about yourself? Why do we have this profound inner sense of me, distinct from others?
That ability to reflect on one's own qualities, like, am I introverted, or am I a good listener, or how did I react in that situation, is a crucial defining component of human self-awareness.
Definitely.
A fascinating fMRI study really delved into this, comparing brain activity when subjects were prompted to reflect on their own qualities versus those of an acquaintance, or simply general knowledge.
Okay, comparing self versus other versus general facts.
Right. The researchers were meticulous, carefully controlling for factors like attention, semantic processing, and even the emotional valence of the keywords to ensure the results truly isolated the neural signatures of self-reflection.
So what did they find? Were there specific areas that lit up only for self-thoughts, providing a unique signature of self?
What they discovered was intriguing. Both person conditions, reflecting on oneself and reflecting on an acquaintance, recruited common regions like the medial prefrontal cortex, MPFC, and posterior regions, such as the posterior cingulate cortex.
Okay, so some overlap makes sense.
Right, as both involve thinking about a person or processing social information. However, the left anterior insula showed unique, significant activation, specifically associated with self-reflection.
The left anterior insula, that's specific.
This was a key and highly specific finding, indicating its distinct role.
The insula. Many of our listeners might associate that part of the brain with bodily awareness or strong emotions. So what's its typical role beyond this self-reflection finding, and what does its unique involvement tell us about the nature of self-awareness? Let's pause and simplify that part again.
That's a great question, and it really highlights the insula's multifaceted role. You're absolutely right. The insular cortex is predominantly associated with interoceptive awareness, our conscious sense of the internal state of our body.
Gut feelings, heartbeat.
Exactly, our heartbeat, breathing, gut feelings, and even internal pain. It also plays a crucial role in processing emotional salience, helping us perceive and integrate our bodily sensations with our emotional states.
Right.
So its unique involvement in self-reflection strongly suggests a deep, perhaps fundamental connection between our bodily sensations, our emotions, and our integrated sense of self.
Ah, connecting body and mind for self-awareness.
Exactly. It links our physical being, our visceral experience, to our mental self-perception. grounding our abstract self-concept and our physiological reality. This suggests that our sense of who I am isn't purely cognitive, but deeply embodied.
And when this integration goes wrong, what happens if that insula function, or the broader self-reflection network, is impaired?
Impaired self-awareness is a common and debilitating feature in various psychiatric disorders, most notably schizophrenia, but also in conditions like autism spectrum disorder.
Okay.
In schizophrenia, for instance, prefrontal and cingulate regions involved in self-reflection are often compromised. If you can't accurately perceive or reflect on your own mental or emotional states, it profoundly impacts your experience of the world and yourself.
How so?
Patients might struggle with understanding their own intentions, recognizing their own thoughts as distinct from others, or recognizing their own emotional expressions. This leads to significant psychological disturbances and a fractured sense of self, underscoring the insula's critical importance for healthy mental functioning and a coherent personal identity.
So, the brain clearly has specific networks for self-reflection. But what about when our minds wander, or we're just resting, not actively doing a task, but perhaps daydreaming, remembering the past, or planning for the future? Is there a brain network dedicated to this kind of internal self-referential thought, our brain's equivalent of an idle state?
Yes, that's precisely where the default mode network, or DMN, comes in.
The DMN. Heard a lot about that one.
It's a constellation of highly interconnected brain regions, primarily the medial prefrontal cortex, MPSC, posterior cingulate cortex, PCC, and inferior parietal lobule, IPL, along with parts of the hippocampus and angular gyrus that consistently activate when we're not focused on an external task.
Their resting state network.
Exactly. It's so reliable that it's often called the resting state network because it becomes most active during periods of apparent mental rest.
It's like our brain's default setting, like when your computer goes into screensaver mode, but it's still doing background tasks, processing internal data.
Exactly. And it's important to note that it's often anti-correlated with task-positive networks, which activate during demanding cognitive tasks.
Ah, so one goes up, the other goes down.
Generally, yes. So when your brain is heavily engaged in solving a complex puzzle or focusing on an external stimulus, the DMN tends to quiet down, and when you're relaxing, mind-wandering, or engaging in introspection, the DMN becomes highly active.
Interesting.
This isn't just a baseline of inactivity. It's indicative of deep, almost architectural features of reflective consciousness. Its activity patterns suggest a dynamic and highly organized flow of information, even when we're not consciously directing our attention to the outside world.
So what does the DMN do for us? What kind of mental processes does it support when we're in this default internally focused mode?
Its functions are incredibly broad and absolutely crucial for our rich internal mental life. They include autobiographical narrative.
Our life story.
Exactly. How we construct and remember our personal story across time, perspective memory.
Thinking about the future.
Right. Our ability to think about the future, plan and simulate scenarios, and critically, theory of mind, Tom, our capacity to understand others' intentions, beliefs, and emotional states.
Wow, that's a lot.
It is. The DMN is fundamental for the conscious integration of experience into a coherent self-narrative, helping us set the spatiotemporal and intersubjective associations between our experiences. It's involved in evaluating our place in a social hierarchy and continuously updating our personal and social narratives, essentially figuring out where we stand in the social world.
That's fascinating. So it helps us understand our place in the world and our social interactions. It sounds like it's continuously constructing our sense of self within a social context, creating a mental map of our social landscape. That's a great question. Let's break it down.
Precisely. The MPFC, a key node in the DMN, is highly susceptible to social cues and interaction. It helps set the social frame for what is salient in an interaction and preload socially appropriate behaviors.
Setting the social frame.
Yeah. Think of it as continuously updating your personal and social narrative, evaluating your place in a social hierarchy. This network is how we interpret our role as an agent within unfolding social interactions, managing complex linguistic content, interpreting eye gazes, and understanding body postures to determine the mood of a room. It's essentially your brain's social compass.
And if the DMN is impaired or its connectivity goes awry, does that affect these core self and social abilities?
Absolutely. Abnormal connectivity or activity within the DMN is strongly linked to thought disorders and internalizing conditions such as schizophrenia, obsessive-compulsive disorder, OCD, and depression.
Ah, okay.
These conditions are often construed as self-related reflective thought disorders, where individuals struggle with coherent self-narratives, become trapped in repetitive thoughts, or have difficulty accurately understanding social cues and emotional states in others.
Sure, like getting stuck in negative thoughts and depression.
Exactly. For instance, in depression, the DMN can become hyperactive, leading to excessive rumination on negative self-thoughts, underscoring its central importance in maintaining a coherent sense of self and healthy social engagement.
We've heard a lot about the prefrontal cortex, or PFC, in relation to various theories of consciousness. But what's its specific, nuanced role in self-awareness and social behavior, especially when it comes to understanding others and then adapting our own behavior?
Right, the PFC, it's universally recognized as a key area for the social brain, our sophisticated capacity to recognize and infer the content of other minds, to empathize with them, and crucially, to use that understanding to predict future behaviors and behave in socially appropriate ways.
The social conductor.
Yes, it's the conductor of our social orchestra, allowing for complex social cognition beyond mere reaction.
So the PFC helps us be socially appropriate. It's like our brain's social etiquette guide, giving us the flexibility to respond appropriately in different social contexts.
Yes, that's a good analogy. Specific subdivisions within the PFC, such as the orbitofrontal cortex, or OFC,
OFC.
and dorsomedial prefrontal cortex, or DMPFC,
DMP. Okay.
are particularly involved in theory of mind, Tom, the ability to attribute mental states to oneself and others, and behavioral self-awareness. The DMPFC, for instance, is more associated with the cognitive aspects of self-reference, helping us maintain a consistent view of our own behavior and personality, even evaluating how well we're doing on a task.
And what happens if these areas are damaged? What are the real-world consequences for someone with PFC damage in terms of their social life and their self-perception?
Studies on patients with PFC damage offer stark insights. They often show impaired behavioral self-awareness and significant affective theory of mind deficits.
Affective Tom deficits, so trouble with emotions.
Yes. For example, damage to the DMPFC can lead to overestimation of one's own behavior. Patients may deny apathy or impulsivity, even if their family members report severe, obvious changes.
Wow, they just don't see it in themselves.
Exactly. They literally don't recognize or integrate their own behavioral changes into their self-concept. Damage to the OFC, on the other hand, can profoundly impair affective Tom, meaning they struggle with understanding the emotions of others.
So they can't read the room emotionally.
Right. While they might intellectually grasp the logical aspect of a situation, they struggle with truly empathizing or taking another's emotional perspective.
So this impacts their ability to truly understand themselves and others on a deep emotional level. It makes me wonder about the nuance of human connection without these functions, how much we take for granted.
Yes, it highlights how profoundly these brain regions underpin our most human interactions. The OFC is also famously implicated in the somatic marker theory.
Somatic marker, gut feelings again.
Exactly. It suggests that social decision-making is influenced by bodily states, essentially, a gut feeling or emotional resonance that guides our social choices. Without that somatic marker, due to OST damage, these patients might struggle to make empathic reactions or make socially appropriate decisions, leading to profound difficulties in their personal and professional lives.
Yeah, you can see how that would be devastating.
These studies collectively underline how intimately our sense of self, our social abilities, and our capacity for emotional intelligence are rooted in specific neural architecture and its healthy functioning.
This next section takes us into something that, for many, sounds almost like science fiction, or at least two completely unrelated fields. Quantum biology. Have you ever wondered if the weirdness of quantum mechanics typically seen in the subatomic world could actually be happening inside your brain at the cellular level?
It sounds wild, right? For a very long time, the prevailing wisdom was that the brain, a warm, wet, noisy biological system, was inherently incompatible with delicate quantum effects.
Too messy for quantum stuff.
Yeah. Quantum phenomena like superposition and entanglement usually require extremely cold, isolated environments to maintain their fragile states. But researching quantum biology is dynamically challenging that assumption.
Quantum biology.
It's like a rapidly growing interdisciplinary field that suggests quantum phenomena might actually play a crucial, non-trivial role in fundamental biological processes, potentially offering novel explanations for their extraordinary efficiency.
So quantum effects aren't just for super cooled labs and physicists anymore. They could be happening right inside us, influencing fundamental life processes.
Exactly. There's mounting evidence suggesting quantum coherence plays a role in the extraordinary efficiency of photosynthesis.
Photosynthesis.
Really? Yeah, allowing plants to capture light energy with near-perfect precision without losing it as heat. And even the avian compass, which birds use for navigation during their incredible migrations, has compelling evidence suggesting it exploits quantum entanglement to sense Earth's magnetic field.
Birds using quantum entanglement. Mind blown.
Right. Researchers are now scrutinizing other biological processes like olfaction, our sense of smell, enzyme catalysis, the speed of chemical reactions in our bodies, and even the intricate processes of DNA repair for similar effects. The leap to the brain, while still the most speculative area, isn't as far-fetched as it once seemed.
This leads us to one of the most intriguing and certainly controversial theories attempting to bridge this gap. Orchestrated objective reduction, or ORCH, or R. It's definitely got a catchy name.
Indeed, this theory, developed by the brilliant Nobel Prize-winning physicist Roger Penrose and anesthesiologist Stuart Hameroff,
Penrose and Hameroff, right?
proposes that consciousness arises not just from classical neuronal firing, but from quantum computations occurring within structures called microtubules inside our neurons.
Inside the neurons themselves.
Yeah. It's an ambitious attempt to link the fundamental laws of quantum physics directly to the subjective experience of consciousness, bypassing many of the hard problem issues faced by purely classical theories.
Microtubules. Many of us might remember them from biology class, maybe something about cell division. Let's pause and simplify that part again. What are those, and why would they be so central to a theory of consciousness?
That's a critical question. Microtubules are dynamic protein structures found in all eukaryotic cells, from plants to humans. They're essentially tiny hollow cylinders.
Okay, tiny tubes.
And they have a variety of functions.
Yeah.
They're integral to cell division, forming the spindle apparatus, and they act as tracks along which motor proteins move cellular components and neurotransmitters within the cell.
Like little highways inside the cell.
Exactly. ORCH focuses specifically on those found in the dendrites and cell bodies, soma, of nerve cells. Microtubules in these areas are less regularly arranged compared to those in axons or non-neural cells, forming what Hameroff and Penrose refer to as recursive networks that they suggest are remarkably well-suited for complex information processing and learning.
Recursive networks. Interesting.
They are also notably more stable, often protected from disassembly by specialized microtubule-associated proteins.
And how do they relate to quantum effects? What's the connection there?
The theory suggests that tubulin dimers, the proteins that make up microtubules, can exist in a superposition of mechanical conformations.
Superposition, being in multiple states at once.
Right. In this state, they effectively act as biological qubits, the basic unit of quantum information, capable of existing in multiple states simultaneously until measured or collapsed.
Biological qubits.
Wow. The orchestrated objective reduction part refers to Penrose's idea that these superpositions spontaneously collapse due to a fundamental, non-computable process in the fabric of space-time, specifically related to objective gravity thresholds.
Okay, that's getting deep into physics.
It is. These discrete, self-organizing collapses occurring rapidly are what ORCH proposes constitute individual moments of conscious experience, creating what we perceive as a continuous stream of consciousness.
But quantum effects are famously fragile, susceptible to decoherence. That's when a quantum system interacts with its environment and loses its quantum properties, essentially becoming classical. How can they last long enough in a warm, wet, and inherently noisy brain to matter for consciousness? I remember Max Tegmark calculated they decohere almost instantly.
That's precisely the biggest challenge, and the source of much of the controversy around ORCH.
The decoherence problem.
Right. Initial calculations by physicist Max Tegmark in 2000 suggested decoherence times for quantum states in the brain were indeed far too short, on the order of 1013 to 1020 seconds, making it seem impossible for quantum effects to play any role in macro-scale cognitive processes.
Like way too short.
Way too short. However, Hameroff and Penrose, along with other researchers like Hagen et al., countered that Tegmark had based his calculations on a simplified model that did not accurately resemble their proposed microtubule system.
They said the model was wrong.
Essentially, yeah.
They?
Specifically ignoring the protective environment within the microtubule's hydrophobic core and the specific type of quantum dynamics involved. Later recalculations, using more refined models that incorporate the unique structure of microtubules, have shown significantly longer coherence times.
Longer, but how much longer?
Potentially long enough for biologically relevant quantum processes to occur. The debate continues, but the core challenge of maintaining coherence in a warm, wet environment remains a major hurdle for any quantum theory of consciousness.
What's the real-world implication here, beyond the theoretical physics? Are there any connections to things we actually experience or medical phenomena?
It's fascinating that certain chemicals known to profoundly influence consciousness, like general anesthetics and certain antidepressants, are known to interact specifically with microtubules.
Anesthetics interact with microtubules. Interesting.
Yeah. Some researchers, like Craddock et al., suggest that anesthetic gas molecules binding inside the hydrophobic channels of microtubules might inhibit these proposed quantum effects and disrupt coherent energy transfer, thereby explaining their profound effects on consciousness, essentially turning off awareness. They draw a compelling comparison to quantum beats observed in light-harvesting complexes of plants, where quantum coherence enhances efficiency. They even argue that tryptophan residues, which are amino acids present in tubulin proteins, could act as quantum channels for electron transfer within microtubules.
Tryptophan, like in up your
The very same amino acid, yeah.
Yeah.
Acting potentially like quantum wires, similar to the processes seen in photosynthesis.
So if this theory holds, anesthetics might literally be turning off quantum consciousness by interfering with these specific quantum processes within our neurons. That's a wild thought and a potentially testable one.
It's one of the most direct and testable predictions of the Oort-Shor theory. Further experimental observations support this, such as findings that certain xenon isotopes with non-zero nuclear spin have a notably lower anesthetic effect compared to other isotopes with zero nuclear spin.
Whoa, depends on the isotope spin.
Exactly. This suggests a spin-dependent quantum mechanism at play, which aligns with Oort-Shor's hypotheses about quantum information processing.
This next hypothesis gets even weirder, delving into neural entanglement that suggests quantum coherence could last for hours or even days in the brain, which seems to fly in the face of everything we just discussed about decoherence. How could something so fragile possibly persist for so long?
This is a bold hypothesis from Matthew Fisher, a quantum chemist.
Okay, Matthew Fisher.
He proposes that the nuclear spin of phosphorus atoms might function as a neural qubit.
Phosphorus spin, okay.
He suggests that specific calcium phosphate clusters, called Posner molecules, which are tiny, sub-nanometer-sized spherical structures.
Posner molecules, never heard of them.
Tiny things. 6 calcium ions at each vertex, and 6 phosphate ions on each face. He thinks they could harbor entangled phosphate spins. These could then interact to form larger, entangled Posner molecules.
Entangled Posner molecules. And these tiny molecules could stay quantum entangled for days in the brain. How does the warm, wet, messy biological environment not instantly destroy that entanglement? Given the decoherence problem we just discussed, it seems like a huge challenge.
That's the crux of Fisher's argument. He proposes a unique shielding mechanism.
Shielding? How?
He argues that the rapid tumbling of Posner molecules within the brain's wet environment causes the average magnetic fields from surrounding water protons to effectively cancel out.
So the tumbling averages out the noise.
That's the idea. This sophisticated dynamic shielding, he suggests, would protect the phosphorus nuclear spins from environmental interference, significantly extending coherence times. He estimates this coherence could last for hours, or even up to an astonishing 21 days.
21 days? That seems impossible.
Which would be truly groundbreaking for a biological system. While many researchers acknowledge the existence of long-lived nuclear spin states in certain contexts, they often challenge Fisher's assumptions about how easily such ideal, decoherence-protected conditions could be consistently maintained in the complex, uncontrolled biological environment of a living brain.
Right. It needs proof.
Absolutely. It's a hypothesis that requires robust experimental verification.
That's incredible to consider. But what's the proposed biological function of these hypothetical long-lived quantum states? Why would the brain go to all that trouble to maintain them?
Fisher hypothesizes that these entangled Posner molecules are taken up by neurons, specifically presynaptic glutamatergic neurons.
Neurons that release glutamate.
Right, through a process called vesicle endocytosis. Once inside the acidic environment of these vesicles, the unique entanglement of their spin and rotational states could lead to a correlated release of calcium ion.
Calcium release. That's key for neurotransmission.
Exactly. This calcium release, in turn, stimulates exocytosis and further release of glutamate, a key excitatory neurotransmitter. So the theory proposes that these quantum effects could be influencing fundamental neural communication, potentially mediating processes like memory formation and long-term potentiation, where synaptic connections are strengthened.
So quantum effects influencing how memories are formed. Wild.
Very wild and still very theoretical.
Let's switch gears to something we all experience every day. Smell. Our sources suggest even olfaction might have a quantum twist beyond the simple lock and key model that many of us learned in school. I thought smell was just about a molecule fitting into a receptor like a key.
That's the conventional story, yes. Smell and even some aspects of neurotransmission are explained by a lock and key mechanism. Specific odorant molecules fit into specific receptors based on their precise shape, much like a key fits into a lock. This triggers a signal, but an alternative vibrational theory of olfaction, first proposed by physicist Malcolm Dyson in the 1930s and later championed by Luca Turin.
Luca Turin, right? The perfume guy.
That's him. Suggests a more nuanced mechanism. This theory posits that the vibrational frequency of an odorant contributes significantly to how we smell it.
Vibrational frequency.
Yeah. It's not just the shape, but how the molecule wobbles or vibrates, which allows for quantum tunneling of an electron at the receptor site, essentially reading the molecule's vibrational signature.
So it's not just the shape, but how the molecule wobbles its quantum vibrational fingerprint. That sounds like a subtle but profoundly different way for our bodies to interact with the world.
Yes, exactly. And there's some compelling experimental evidence for this. Studies have shown that animals like fruit flies and even lake whitefish can differentiate between deuterated odorants and their non-deuterated counterparts.
Deuterated meaning heavier hydrogen.
Exactly. Deuteration is a process where some hydrogen atoms in a molecule are replaced with heavier deuterium atoms. This changes their mass and thus their vibrational frequency. But critically, it does not change their overall shape.
Ah, so same shape, different wobble.
Precisely. If olfaction were purely lock and key, these animals shouldn't be able to tell the difference. Turin and his colleagues have even found that deuterating certain molecules like histamine can actually increase its binding affinity to its receptors, further supporting the idea that vibrational signatures are at play.
That sounds like strong evidence for the vibrational theory. Does it definitively prove it?
It's certainly compelling, and it forces us to reconsider the traditional model. However, there's still an ongoing debate. Some researchers argue that the effects seen in deuterated odorant experiments could be explained by a nuclear quantum effect, governed by subtle differences in hydrogen bond strength.
Okay, a different quantum explanation.
Not necessarily by direct vibrational tunneling in the receptor itself. So while it's quantum in nature, the exact mechanism is still under scrutiny. Both theoretical and experimental results on vibrational theory and neurotransmission are still inconclusive.
What are the implications for us, especially for medicine and drug discovery, if this vibrational or quantum mechanism is truly at play in how we smell or how neurotransmitters work?
It's incredibly important because these receptors, called G-protein-coupled receptors, or GPCRs.
GPCRs, huge drug targets.
Exactly. They are not just for smell. They are the targets for approximately 1/3 of all pharmaceuticals on the market today.
Wow, a third.
Yeah. Understanding whether they act as sophisticated electronic devices that sense quantum vibrations and tunneling rather than just simple lock and key mechanisms could revolutionize drug discovery. It opens up entirely new avenues for designing medicines that precisely target not just the shape of a binding site, but the dynamic vibrational properties of molecules, potentially leading to far more effective and specific therapies.
That would be huge. And we're also talking about light coming from the brain. BioBits indeed. That sounds almost unbelievable, like our brains are subtly glowing.
Yes, biophotons are known to be produced in brains and other biological systems. These are ultra-weak photon emissions.
Tiny flashes of light.
Exactly. Essentially, tiny flashes of light stemming from metabolic processes. Their intensity has been found to correlate with neural activity and oxidative dysfunction in rat and mouse brains.
Correlated with brain activity. Interesting.
There have even been some speculative attempts to link biophoton emission to human intelligence. Glutamate, a key excitatory neurotransmitter, can actually mediate their production, suggesting a direct link to neural communication.
And these biophotons might have a function. It's not just a byproduct of metabolic activity like a biological exhaust fume.
While their precise function is still under active investigation, it's been proposed that microtubules near mitochondria might absorb and channel these biophotons in a quantum-coherent manner.
Microtubules, again, channeling light.
Potentially. Mitochondria themselves, famously known as the powerhouses of the cell responsible for energy production, are thought to be the main source of biophotons, especially during the complex oxidative processes in their electron transport chain. The idea is that these photons could facilitate rapid, non-local communication within neurons or even across different neurons.
That's fascinating. Does this have any practical applications, perhaps in therapies for brain disorders?
Definitely. Photobiomodulation, which involves the therapeutic application of low-power infrared light to the scalp, is a burgeoning field.
Light therapy for the brain.
Yeah. It's been shown to improve attention, memory, executive function, and even rule-based learning in various studies, and is being explored for conditions like Alzheimer's and traumatic brain injury.
How does it work?
While the exact mechanism is still unclear, the mitochondrial electron transfer chain is a likely site of effect, involving chromophores like tryptophan.
Tryptophan again?
Yep, which can absorb light and potentially enhance cellular energy production or signaling.
So light therapy could potentially be boosting our brain power and function. That's amazing. And it ties into another area of quantum biology, magnetic field effects. Our sources suggest even Earth-strength magnetic fields can influence our brain.
That's right. Studies have shown that even relatively weak Earth-strength magnetic fields can subtly decrease alpha-frequency brain waves.
Alpha waves, the relaxed wave.
Exactly. Which are typically associated with a relaxed, awake state and the brain's readiness to process external stimuli. This suggests our brains are far more sensitive to these subtle environmental cues than we previously thought.
How does that work? Why would a magnetic field, so weak we don't even consciously perceive it, affect our brainwaves?
Researchers initially speculated it might be due to ferromagnetism within the brain, perhaps from trace amounts of magnetic particles.
Like tiny magnets in the brain?
Possibly. But a more compelling and widely discussed hypothesis involves the radical pair mechanism.
Radical pairs. Sounds reactive?
It involves electron spins. This intricate quantum mechanism, also seen in the hyper-efficient processes of photosynthesis and bird navigation,
Birds again?
involves the spin dynamics of electron pairs. When two electrons become briefly paired, their spins can be influenced by external magnetic fields, altering the outcome of biochemical reactions.
Okay.
For instance, in photosynthesis, this mechanism acts as a quantum protective mechanism to reduce harmful reactive oxygen species, or ROS,
ROS, the damaging molecules.
right, which are toxic to living cells. If ROS production is linked to the generation of certain brain waves, like alpha waves, then radical pair dynamics influenced by geomagnetic fields could provide a plausible quantum explanation for how these fields subtly influence brain activity and perhaps even our cognitive state.
Wow.
It's as if our brains are subtly interacting with the Earth's magnetic field through these incredibly tiny yet profound quantum processes. What do you think with that?
That's just wild to consider that our very consciousness, our internal experience, might be influenced by the Earth's magnetic field through these incredibly tiny quantum interactions. It makes you realize how interconnected everything is, from the subatomic to the planetary scale. So we've talked about what consciousness might be and how it works in a healthy brain, even delving into quantum possibilities. But what happens when it breaks down? How do we truly understand patients in disorders of consciousness, like those in a coma or a vegetative state, especially given the ethical weight of misdiagnosis?
These conditions, such as vegetative state unresponsive wakefulness syndrome, VSUWS, and minimally conscious state, MCS, represent severe disruptions of the neural networks supporting both arousal and awareness.
Arousal and awareness, yeah.
They are still poorly understood in terms of their precise neurobiology, the extent of underlying awareness, and the pathways for potential recovery. These patients present not only a significant diagnostic challenge, but also profound ethical dilemmas for their families and medical teams.
Right.
The high rate of misdiagnosis we discussed earlier, where nearly half of patients initially classified as VSUWS may actually possess some level of consciousness, underscores the urgent need for more objective assessment tools.
And it's precisely because it's so hard to tell who is truly conscious and who isn't, purely through behavior, that neuroimaging becomes so vital.
Exactly. Standard behavioral scales like the Coma Recovery Scale Revised, CRSR, are crucial and considered a gold standard for bedside assessment, but they rely entirely on observable responses and can still miss subtle non-motoric signs of awareness.
They miss the hidden consciousness.
Exactly. This limitation has fundamentally driven the development and application of neuroimaging techniques, like fMRI and PET. As we discussed, these have been truly transformative, revealing covert consciousness, brain activity patterns, consistent with awareness, even when patients show no outward behavioral signs.
Right, like the tennis imagining test.
That's a huge area of current research and a new frontier in neurological rehabilitation. One of the most promising avenues is non-invasive brain stimulation, or NIBS.
NIBS, okay.
These are pain-free and safe techniques that don't require surgery, like transcranial direct current stimulation, TDCS, and transcranial magnetic stimulation, TMS.
TDCS and TMS.
They can be applied right at the bedside or in a rehabilitation setting, making them highly accessible.
How do they work? Are they like tiny, precise electrical or magnetic nudges to the brain?
That's a good way to think about it. TDCS uses weak electrical currents to modulate neural activity, either exciting or inhibiting specific brain regions by altering neuronal membrane potentials.
Gentle currents.
Yeah. TMS, on the other hand, uses rapidly changing magnetic fields to induce electrical currents in targeted areas, directly stimulating or suppressing neuronal firing.
Magnetic pulses.
Right. By precisely targeting key regions and networks, for instance, the prefrontal cortex or components of the DMN that are known to be disrupted in DOS-C, they can influence brain network function.
Targeting the affected networks.
Exactly. The goal is to rebalance or jumpstart activity in underactive areas, or quiet down overactive ones, attempting to restore more functional neural communication. Studies have shown they can significantly improve arousal and alertness in some patients with DOS-C.
And what are the tangible benefits for patients? Can these techniques really make a difference in their recovery trajectories?
The potential benefits are immense. Promoting early awakening from unconscious states can significantly protect patients from long-term disability and even reduce mortality after severe brain injury.
Wow, so it's really critical.
It is. Clinical trials have demonstrated that TDCS, often combined with physical therapy or cognitive training, can significantly improve clinical scores on consciousness assessments in patients recovering from stroke, traumatic brain injury, or even anoxic brain injury.
Combined with rehab, yeah.
It offers a non-invasive, relatively low-risk path towards promoting recovery and potentially unlocking that hidden consciousness, allowing some patients to regain a level of communication or responsiveness they previously lacked.
This next concept is quite abstract, but our sources mention something called temporal brain dynamics asymmetry as a signature of consciousness. It sounds like something out of a deep physics textbook. Can you explain what that means for our brains?
That's a brilliant question, and it indeed ties into fundamental physics, specifically the arrow of time and thermodynamics.
Arrow of time. Okay, I'm listening.
Imagine a system at equilibrium, like a perfectly still pond. Its dynamics are reversible. You're just as likely to see a ripple unfold forward in time as backward, with no net flow of probability or production of entropy.
Okay, reversible, no direction.
But conscious brains are not at equilibrium. They are highly complex, non-equilibrium systems that constantly produce entropy and exhibit irreversible dynamics.
Irreversible, so there is a direction.
Exactly. This establishes a favored direction in time for information flow, the arrow of time, meaning brain processes unfold in a unique, non-random, and highly complex sequence.
So for our brains, what does this arrow of time imply? How does it relate to being conscious, to our active thinking and perceiving?
Healthy, conscious brains show a clear temporal asymmetry. Their neural activity patterns are fundamentally irreversible. They are far from thermodynamic equilibrium, constantly producing entropy as they process information and learn.
Constantly creating order or complexity.
Right. This indicates a complex, dynamic, and non-random flow of information, a system actively engaging with, transforming, and predicting its environment. It's a signature of highly organized and purposeful information processing, where signals don't just bounce back and forth randomly, but move in a structured, directional manner that builds and updates our conscious reality.
Okay.
We can measure this by looking at the predictability or complexity of brain signals over time using sophisticated algorithms.
And in impaired consciousness, like a vegetative state where that rich internal world seems absent, does that temporal asymmetry disappear?
Exactly. Studies using EEG and fMRI have found a striking correlation. States of impaired consciousness, such as the SUWS, show a dramatic lack of this temporal asymmetry.
The arrow gets weaker or disappears.
Pretty much. Their brain dynamics tend to be far more reversible, closer to equilibrium, with less complex and less directed information flow. This suggests a profound loss of complex, organized information processing, regardless of the specific brain lesion causing the impairment.
Wow.
The brain's activity becomes more predictable, more static, losing that dynamic, forward-moving quality characteristic of conscious thought and complex cognition. It's as if the brain is stuck in a loop, unable to generate novel, complex, or irreversible patterns of activity.
So you can essentially tell how conscious someone is by measuring how random or ordered or perhaps how dynamic their brain signals are over time. It's almost like measuring the life or the narrative coherence of the brain activity itself.
In essence, yes, it's about the directionality, complexity, and non-predictability of information flow. This concept could provide a novel, objective, and quantitative way to distinguish levels of consciousness, even for patients whose specific brain damage varies wildly.
A universal marker, potentially.
Potentially. It's a powerful tool, not just for diagnosing, but potentially for monitoring recovery and the effectiveness of therapies for disorders of consciousness. It's a measure that cuts across specific brain regions and instead looks at the fundamental dynamics of the system.
Right.
This raises an important question. If we can quantify this arrow of time in the brain, and we see it diminish with impaired consciousness, could we one day understand it well enough to actively manipulate it, to restore function, and perhaps even enhance consciousness?
Could we push the brain back towards that complexity?
Exactly. Could we, metaphorically, push the brain further away from equilibrium to reestablish that crucial arrow of time?
Wow, what an absolutely incredible deep dive into consciousness. We've journeyed from the big foundational theories trying to explain how our brains light up with awareness, like Global Workspace Theory and integrated information theory.
The spotlight and the teamwork theories.
Right. To the mind-bending, almost unbelievable possibilities of quantum biology operating within our very neurons, and then into the critical, compassionate work of detecting and potentially restoring consciousness in patients with severe brain injuries.
Indeed. We've explored how concepts like self-reflection are rooted in specific brain regions like the anterior insula, connecting our physical sensations to our sense of self.
Yeah, the embodied self.
We've seen how the default mode network tirelessly constructs our inner narrative, our memories, and our understanding of others, and how our brains are constantly making intricate predictions to navigate the world and build our subjective reality. These networks are truly fundamental to our sense of self and our social interactions.
And the idea that tiny quantum effects, from protein structures called microtubules to enigmatic Posner molecules to the subtle vibrations of odorants, might play a role in everything from anesthesia to our very sense of smell.
Yeah, the quantum wobbles.
Or even how our brain interacts with Earth's magnetic field is truly mind-blowing. It really makes you rethink what's possible at the small scales of our biology and how fundamental physics might underpin our subjective experience.
This discussion highlights just how much more there is to learn in this rapidly evolving field. The adversarial collaborations are refining our theories, pushing them to be more testable and robust, forcing us to confront difficult truths in the data.
Right, but the science is working.
And new insights into fundamental brain dynamics, like the arrow of time, are opening doors for more precise, objective assessments and innovative therapies for disorders of consciousness. The field is truly exploding with new discoveries, challenging long-held assumptions at every turn.
So what does this all mean for you, our listener, as you go about your day experiencing the world around you?
It means that the inner world you experience every single moment, your thoughts, feelings, perceptions, and your very sense of being is far more complex, dynamic, and fascinating than we've ever imagined.
Yeah.
Research is increasingly hinting at an incredible interplay between macro-scale neural networks and potentially profound micro-scale quantum phenomena, suggesting that our consciousness might be woven into the very fabric of reality in ways we're only just beginning to grasp.
Here's where it gets really interesting, something to mull over. If consciousness is, in some sense, buildable, if it arises from complex information processing and intricate internal models, as theories like attention schema theory suggest.
Like it's computable, maybe.
Right. How will that change our understanding of ourselves when artificial intelligence becomes truly advanced? Will AI one day claim to have subjective awareness?
Oof, the big question.
And if it does, what will its unique internal models, perhaps unconstrained by biological evolution, allow it to experience and describe? How will we verify its claims? It's a question that pushes the boundaries of philosophy and science, and one that we may face sooner than we think.
Definitely food for thought.
Thank you for joining us on this incredible deep dive into consciousness. We hope you feel a little more well-informed and perhaps a little more amazed by the universe inside your own head.
Thank you for joining again.